So our rate of change would be changing our price, so 0.63 minus 0.41 over. Since we're dealing with the 2000s, I'm just going to use my years as 23 and 7. All right, so that would make the year 2000 0. Does that make sense? Okay, so 23 minus 7, and we simplify that, we're going to get a nice decimal, 0.01375. Okay. So if they continue at a current rate, how much will it cost in 2035? Thoughts on how we might get there?
You multiply that by 12 and add 0.63.
Okay, you multiplied it by
12. What's the difference in 35 and 23?
okay, and then add it to 63. All right, that works. So if we multiply it, there's 12 years difference between 23 and 35. So 12 times 0.01375. So that's how much change, and we'd add it to 63 cents. What do we get? All right, 0.83. So our new stamp will cost 83 cents. And I concur. Anybody do it differently? Okay, but that works. What'd you do?
Multiply by 35.
Okay. You should still get there in the same, what you use as your starting point, though. Okay. Now, in what year would you expect a forever stamp to cost $1? How might we go about that? Yeah.
You could find what it cost in 2000.
Okay, so we could find what it cost in 2000. All right, and how would you go about that?
I would use that cost as the y-intercept.
Yeah, like where it started? All right, plug it into the calculator that way. Okay. What'd you get?
I got 2050.
Okay.
2050.
2050. All right. Is that what you got? Anybody else get anything different? So looking at that change, could we find the difference between 83 cents and $1? And then divide it by the rate of change and then add that many years? That would work too, right?
I did it by finding the difference between 41 cents and $1 and then adding those years to 2007.
2007? Yeah, that works as well, right? So we could find the difference if I took $1 minus the 41 cents. That gives me,
59.
thank you. Okay. And then if I divide 59 by my rate of change, that should tell me how many years. Okay. I need to add, all right, to 2007. All right, which if I'm going to get 50, it should be 43. All right, so that should tell me that I took 43 years, add it back to 2007, and we get 2050.
I got a 2047.
Okay, how'd you
So
do
I
it?
got the difference between 0.83 and 1.
Mm-hmm.
1.17, and I divided it by the rate of change. And that was just one per year, and I got like 12.3 on top of 2035, which is 2047.
Okay, and so that gave you, what'd you say it was?
Like 12.36. Yeah, 12.36 would be.
Okay, so then if we added that to 2023,
Yeah, it's 2035.
okay, so which one's right?
You would add the 12 to 27.
Oh.
If you had 13, it has to be $1 more. So it'd be 2048.
Okay. What do you think? I would actually take either answer. Okay? All right. I would actually take, y'all were looking at me like I was about to, cut your fingers off or something. All right. So we're just looking at growth there. All right. Linear growth. Probably it's not increasing linearly. Let's just be real honest about that. But All those processes are good thought processes in terms of how they would work. You could generate an equation, you could use point slope form, whatever you want to do, and then plug in one for y. That works too. You could put it in a calculator. I mean, there's just a lot of different ways to approach that problem, okay? But now let's look at the second one. It says the function f of x equals 300 times 1.06 to the x. It models his investment in a stock fund as a function of time in years. Which of the following is true? It is C, okay? It is C. He initially invested $300 and his money increased by 6% each year. So then why, if it's increasing by 6% each year, is this number 1.06? Yeah, we keep 100% plus an additional 6%. Good. All right. So you do remember things about linear and exponential functions. Yay. All right, so that should help us today. We're going to talk about arithmetic and geometric sequences, mathematically and in context, and then construct functions that are comparable to arithmetic and geometric sequences, and then talk about similarities and differences between linear and exponential functions. So like I said, I hope a lot of this feels like review, but here we go. It's just been a Harry Potter kind of day. All right, so let's talk about an arithmetic sequence, okay? Arithmetic means that the properties of each successive term is that it changes linearly, right? All right, we're going to add or subtract something every time we say that it has a common difference. We call that common difference D. Very creative. Okay, so they have a common difference that we refer to as D, which also implies that it has a constant rate of change. So arithmetic sequences change. We either add or subtract something each time, or a constant rate of change, which implies that it is linear. Now, if we want to find a term in a sequence, there are a couple of formulas we think about. Here's the first one, A sub n, so that's any term in the sequence, equals A sub 0 times the common difference and the number of the term, all right, which is what we kind of just did with the stamp problem, okay? The only thing I would caution you about is that A sub 0 is the 0th term, okay? That's a cruel word, not the first term. Okay, so always remember that. A sub 0 is the 0th term, not the first term. So if they give you a list, that's term 1, all right, not term 0. So you might have to go backwards to find term 0. All right, so there's one way to write an equation. Second way that we can write an arithmetic sequence, right, is using something like this. A sub n equals A sub k plus my common difference times n minus k, where A sub k is the kth term. All right. I love all how we say that, kth. All right. formal mathematics. We love all the subscripts and the variables and the weird words. All right, good times. I know y'all aren't the weathermen, but is it supposed to rain today? It's super gloomy outside. I don't do gloomy. And then yesterday was beautiful, by the way. Were you able to get outside a little bit? Oh, it was gorgeous. It was gorgeous. Except I'd made chili for dinner, and so that didn't really go with 75. So anyway, it was okay. All right.
It was 91.
Where's it 91? Where'd you say it was 91?
I was telling her that our game, we were losing 9-1.
Oh, but you didn't lose 901. Okay, that's good.
It was
I was like, let's go where it's 91. Like, I like the hot, as long as there's a beach and, you know, just saying. All right, so let's take a geometric sequence, arithmetic sequence 3n plus 1. And we just want to plot the first few points. All right. Can we plot the 0th term this time? Sure. We've got n and a sub n. So if I want the 0th term, I'm just going to plug in 0. What did it give me? 1. If I plug in 1 for the first term, what would that give me? 4. And let's just do one more. If I plug in 2, 7. Okay. So we could plot those points 0, 1, 1, 4, 2, 7. What do we notice about that function? It's linear, okay? So that arithmetic sequence is linear. Now, something that you need to remember is that sequences are discrete, okay? Yes, we write linear-looking formulas to them, but their domain are distinct whole numbers, 0, 1, 2, 3, 4. So we don't connect the dots, all right? So they are discrete, independent values, right? Not connected. All right. Nice, cute little line there. All right, let's jump in here. Let's get to the good stuff. So here's a sequence, 2, 5, 8, 11, 14. Okay. Is it arithmetic? Do what?
Yes.
We're either add or subtract to get to the next number. Okay? Are we adding or subtracting to get to the next number? Yes, we are. All right. So it is indeed arithmetic. Yay. What is our common difference? What are we doing each time? We're adding 3. Okay. So the list that they gave me there starts with the first term. If I want the 0th term, what am I going to do? Subtract. And so what's that going to leave me with? -1. Okay, so now we know the 0th term, we know the common difference. Can we write a generalized function? And the answer is yes. A sub n is going to equal my 0th term plus my common difference times n. Yes, ma'am.
Does it always start with the second, like,
Always starts with term 1.
okay.
Yes. Good question. All right. So if we have a rule, can we find the 25th term? Sure. A sub 25 will be -1 plus 3 times 25. And what would that yield? 74.
Why is it 3 times?
Because we're adding 3 each time. That's our... My husband just sent me something and said not to play it out loud.
I'm confused where you got the -1.
Because I did the common difference going the other way to find the 0th term. So if I add 3 going forward, subtract 3 going backwards. Okay? That makes me very nervous. Okay. I'm like, usually we send dog memes. Okay, anyway. Because now that I have a pity, I really want a full-blooded pit because he's so fluffy. Anyway, and I buy him pajamas, and he loves them, and he's so cute with his 3 legs. Okay, y'all, this weekend he hurt his single paw on his one leg side, and he was hopping around on 2 feet and not falling over. I was so proud. Okay.
I never had it all with 2 legs.
Really? Yeah, I mean, it's,
And you had another Dollar Tree one.
yeah, maybe it has 3.
Tripod.
Yeah, tripod. Okay, let's look at this one. So it says to plot the first 7 points of the sequence below. We're not going to actually do that because we don't have time, but what are we going to notice about it when we do it? 1, 2, 2, 5. I'm just using the list up here. 3, 8. And so it's linear, okay? For 11, it's linear. Okay, it's linear. All right, if we plotted those points up there from the list, they would be linear, those y values. Let's write a rule using the fifth term. Okay, let's write a rule using the fifth term. Okay, well, first of all, what is the fifth term? It is 14, so we know a sub 5 is 14. That's where we have to start, okay? So we're going to write this generalized rule. So a sub n, right, is going to equal a sub 5 plus my common difference times n minus 5. Well, let's just plug in the values we know. Okay. A sub 5, we said, was 14. Our common difference was 3. And n minus 5. And that's it. That's the second formula. Okay? You take a point that you know, and you plug it in with that common difference. All right. Does that look similar to anything you've ever seen before? When writing linear equations? Okay, we'll keep looking at it. Maybe we'll see it in a little bit. Okay. So let's do this. This time it says just to write the equation for a line. All right, represented by the points on the sequence. We want to use point slope form with the point 514. When I do point slope form, all right, y equals, we usually start with our slope. What's our rate of change for those points? It's 3. We do x minus the x value. And then we keep the y value. All right, point slope form usually has y minus 14. I just do it in one step, move it over. That look familiar? Yeah, it should look exactly like this up here in a little different order. Okay, it's just point slope form. All right, that second form for an arithmetic sequence is just point slope form. All right. So that's just the basic stuff. If we do mathematically based stuff, I give you a list of numbers, we come up with a sequence, we come up with a formula for that sequence, we generate certain terms, et cetera, okay? Now let's look at something that's in context, okay? Something that's in context. So the seating capacity of a civic center with 48 rows of seats has 9 seats in the first row, 11 seats in the second row, 13 seats in the third row. We want to find the total number of seats in the Civic Center. All right, so we got some work to do here. There's a lot of strategies we could use to do this, right? We know that there are 48 rows, all right, to 48, okay? In row 1, how many seats did we have? We had 9, not that. Got excited. We had 9 seats. In row 2, we had how many? 11. And in row 3, we had 13, and the process continues. Okay? So is it increasing at a constant rate? Sure. Okay, so that means it's definitely linear, all right, whatever we're looking at. So we can approach this in a couple of ways, all right? We know that if I use this first point, what's my common difference? Yeah, my difference is 2. It's changing by 2. Can we at least figure out how many are in the last row? Sure. Okay, so we could figure out how many were in the last row, and we would do that. We could create that formula. A sub n is going to equal 9 plus 2 times n minus 1. I just did the point slope formula. Okay, my 9 seats, my common difference, and it was the first term. Okay. And so if we want to figure out for that last row, a sub 48, that would be 9 plus 2 times 47, which is 103. Okay, so the question becomes, what do we need to do to add all that up? All right, because there's a lot of values in between. What are your strategies? What do you think? Yes, ma'am.
Why did you subtract 1 from the
Think about it in point slope term form. Here's your x, here's your y. All right, so it's always x minus whatever the x value is plus the y value. Okay? How might you approach finding out the total number of seats?
No, the explanation point thing.
Well, that's if we multiply, but we're adding. That's a good strategy. That was a good thought. Could we get all 48 rows and add them all up? You could, all right? It's going to take a minute if we do that, though, right? And so we like to know, is there some kind of a shortcut? Anybody remember the shortcut from Algebra 2? Yeah, it's kind of like a summation. There is a formula. It says we do this, n divided by 2 times your first row and your last, plus your last row. Okay, so there is a formula for that. We have 48 total rows. We divide it by 2. My first row had 9. My last row had 103. All right. Now, I don't think they're going to ask you this formula on the AP exam. All right, just so you know. All right. Nor are they going to give it to you if they do. So, all right. And then we would get our answer. What was our total there? Yes, by all means, use a calculator.
2,688.
Yeah, 2,688 seats. What I would anticipate on the AP exam is them being sure that you recognize that that is an arithmetic sequence, possibly finding a specific row or something like that. Okay?
What is that for?
The sum. Yeah, the sum of all terms. Okay.
For that formula, is it 2 every time?
Yes. Yeah, you divide it in 2. And what's cool, if you went back and checked, you can kind of derive that formula. In the second row, there are 11 seats. How many seats would be in the 47th row? Okay, 101. Okay, what's 101 plus 11? What's 103 plus 9? 112. That's where it comes from. We have to do half. Okay, so, all right. Cool beans. Question about that? All right, let's jump to geometric sequences. All right, in just a second, but let's look at a couple more. I'm kidding. Let's do 2 more examples. I forgot. I'm kidding. All right. See what you can do with example 3 and example 4. All right, see what you can do for example 3 and example 4. Go. Heavy sigh, heavy sigh.
Expression.
Several of the terms of an arithmetic sequence are shown above. Find an expression using, then use the expression to find A of 17. Okay, so let's take a look at what we've got right here. They gave me several points. There's 1, there's 1, there's 1, there's 1, there's 1. Did they give me the 0th term? Yeah, they did, okay? So my 0 term is 8. So a sub n's gonna equal 8 plus, all I really need to know now is the common difference. What's the slope? How much did it change by? -2. So I could write that as a sub n equals 8 minus 2n. And then to find my 17th term, 8 minus 2 times 17, and I end up with -26.
Okay, so why did you not do the -1?
Because I know the zero term. If I know the zero term, I don't need the -1. If I started with the 0.16, then I would have used n-1 and started with 6 plus n-1.
So you could have, because I got the same answer.
You would. Mm-hmm. Yeah. So you could have started like this. 6 minus 2 times n-1. It will reduce to the same equation.
Okay.
Yeah. So they both work, which is nice. Okay? All right, so let's look at 4. So it says, let a of n be an arithmetic sequence. They tell me a sub 2 is 7 and a sub 6 is 9. We want to find an expression for a sub n and then use that to find a sub 24. What do I need to find first? The common difference, okay? And to do that, I'm just going to do a rate of change. All right, 9 minus 7 over 6 minus 2. And so I get 3, 2 over 4. Okay, it's only 3 on Thursdays. 2 over 4, which is 1/2. Okay, so my common difference is 1/2. And then we can use one of the points we're given. I typically use the smaller point just because I like smaller numbers. All right, so a sub n is going to equal my value there at a sub 2 plus my common difference. What's going to go in my parenthesis this time?
24.
Nope.
N.
N minus 2 because I started with the second term. Okay, now plug in your 24. A sub 24, 7 plus 1/2 times 22 minus 2. Do you get 70?
Give me 24 minus 2.
Yep, 24 minus 2. I was just, I was excited. It happens. And so we get, 11, 7 plus 18? Much better.
I have a question. Does it make a difference if you just count back to 0 when you do the equation from 0?
Nope, doesn't matter.
That's what I do.
It's fine.
That's the wrong way to do it.
Nope.
Okay. 'Cause
Just takes
mine
more
looks a
work.
little different. Mine looks like 6.
Do you still get 18? And that's all that matters. Okay, yeah. All right. If you want to take the time to count back to 0, that works. To start with your zeroth term. Mm-hmm.
So even if we, because it says to write the sequence with that term,
Mhm.
would it be kind of wrong if we use 6.5?
No. Nope. Okay. All good questions. Okay. All right, so let's jump to geometric sequences and talk about how they change a little bit. Okay. With geometric sequences, we no longer change by common difference. We have what's referred to as a common ratio. Creatively enough, not a ration, but a ratio. We call it R. Okay, we call it R. Or another way that we say this is that we have a constant proportional change. That means multiply or divide. Okay, so there's a common ratio when we talk about a geometric sequence, which means we have a constant proportional change. We just multiply or divide to get to the next term. So again, 2 formulas that we use interchangeably, all right? The first one, if I know G sub 0, all right, G sub E0 times R, our common ratio, to the nth power, all right? Again, G sub 0 is the 0th term, not the first. And then if I don't happen to know the 0th term, all right, I can take G sub k times r to the n minus k. All right, and just scoot it down a little bit. All right. Again, G sub k is the kth term. Right. So what kind of function are we looking at there? Because r is a number, G sub 0 is a number, my variable's in the exponent, so what kind of function is that? No, if my variable's in the exponential, all right, these are exponential. All right, let's start with a sequence. First of all, is it geometric? Okay, am I growing proportionally, meaning I'm multiplying or dividing by something each time? Yes, what am I doing? I'm multiplying by 2, so my ratio is going to be 2. If I ever divide, that ratio is a fraction. Okay, so if I were dividing by 2 each time, my ratio would be 1/2. Okay, what would be my 0th term? If I multiply going forward, what are we going to do going back? Divide. So what would G sub 0 be? 3/2. And so let's write a rule now that we know those two things. So A sub n would equal my G sub 0, my initial value, times 2 to the n. Okay, so using the 0th term. Okay, let's find the 10th term now that we have a rule. So A sub 10, 3/2 times 2 to the 10th. Probably going to be a big number if I had to guess. What'd you get? 1536. Good. Okay. So now it says write a new rule. It's going to still be the same sequence, but this time start with the first term. Okay. Start with the first term. So if we're going to do that, A sub n is going to equal, what is my first term? What value is it? 3. My common ratio is still what? 2. And now my exponent changes to n minus the term I'm on, so n minus 1. Okay. So 3 times 2 to the n minus 1. Okay. It's just exponential. Let's plot those. It says the first 5 terms, but let's just plot those first 4 terms. Okay. Term 1 is 3. Term 2, bless you, is 6. Term 3 is 12. And term 4 is 24. Okay. What do you notice about that graph? Yeah, it's a curve. It's definitely not linear. Okay. It's definitely nonlinear. So let's take a look at several examples, all right, kind of how they might question us in this regard. Okay. So arithmetic sequences changed by a common difference. Geometric sequences changed by a common ratio. Okay. All right, here we go. Let's take a look at this one. Oh my goodness. Fractions. They're the devil. All right. So consider the sequence 5, 5/3, 5/9, 5/27. Is it arithmetic or geometric? It's geometric, okay? Now, I will tell you not to just assume aside that every sequence that has fractions in it is going to be geometric, okay? Sometimes it won't be, all right? But this one is. So that being said, let's find R. What is my R value? How is it changing each time? What are we multiplying by? 1/3, okay? 5 times a third is 5/3. 5/3 times a third is 5/9. Okay, so we're multiplying by 1/3. Let's write a function to model that sequence. Okay, let's write a function to model that sequence. I can go back and get the 0th term if I want, but I know the first term, I know the common difference, we can just write it, okay? So a sub n is going to equal, the first term I saw was 5. My common ratio was 1/3. Because it was the first term, my exponent is n minus 1. Okay? Now, what would the 0th term have been? 15. So you could have also said 15 times 1/3 to the n. Both are equivalent. Okay? Now, question. Is the domain of that function, if I look at that equation as a function, the same as the domain of the sequence? So I'm looking at it two different ways. Once as a function, once as a sequence. Their domains are not the same, okay? The domain of the function is all real numbers. Okay? If it's a function, I care about the points in between. I would connect the dots, right? If it's a sequence, it is discrete. Okay, we'd start at 1, 2, 3, etc. Okay, it would be discrete.
What is discrete?
Means independent points, not connected, nothing in between. Okay, I have the first term, then I have the second term. I have the dots, but not the connection. Okay? What's the growth rate? 1/3. All right, my growth rate is 1/3. Question about any of that?
Yeah,
Okay.
my contact's not
Oh, that's not good.
so, no, I'm good now. I just need to just go back.
Okay. All right, try example 7. That uses the graph. Okay, so let's take a look. Did they give me a 0 term on this one? Yeah, they did. Okay, so it started at 8, then it went to 4, then it went to 2. So what's my common ratio? Is 1/2. Okay, R is 1/2. So we could say G of n equals 8 times 1/2 to the n. Okay, now to find G of 10, your calculator's, because it's a pretty small fraction, it's going to give you probably scientific notation. So let's think for just a second. Will it do 2 to the 10th for you? Okay, what's 2 to the 10th on your calculator?
1,024.
Okay, so that really gives me the fraction 8 over 1024. If you type that in your calculator in fraction form, it will give you the fraction answer back. Okay, so if you do alpha y equals 8 over 1024, it will give you that reduced fraction, which I believe is 1 over 128. Okay. So if you're ever on a section like that and they give you a fraction form versus a decimal approximation on a calculator section, you can get there.
Would you take the decimal form too?
If it was on a calculator section. Okay. All right. Now let's look at example 8. Example 8 is a little bit trickier because unlike linear or arithmetic sequences, when we just know 2 points, it's hard to find that rate of change, okay, because it's not constant. So just doing slope doesn't work, okay? We have to do a little extra something to find the rate, all right? So here's what we're going to do. We're going to start with this point, g of 6, okay? And so we're going to let the equation 128 equal, I'll put in my blanks here, all right? And treat that like my n and my g sub n, okay? However, I'm also going to put my r in that parenthesis, okay? Because that's what I'm solving for. What I'm going to put in front of that is my other ordered pair. I'm going to treat this as my initial amount. And so if I put 3 there, it would be n minus how many in the exponent? 3. Okay, so if I put the third term there, all right? So you let it equal the larger term, all right, which is going to be your n. And then you plug in your lower term in the actual equation, okay? Now, another way to start that might be to look at it like this, okay? Nope, not that. If we had started with g sub n equals negative 2r to the n minus 3, and then I plugged in the point I knew. Okay, so that's what I did. I plugged in g of 6. So 128 equals negative 2r to the 6 minus 3. Okay, so this took me there. I kind of started on step 2. All right, let's simplify a little bit. We're going to have to solve an equation here. So I've got 128 equals negative 2r to the third. How would I solve that equation? What would I need to do? Divide by negative 2. So r cubed is going to equal negative 64. Then what? Take a cube root. And so r is going to equal negative 4. All right, so we had to solve for r. Okay, we had to solve for r because they didn't tell me. Okay, so now we want to go back to this generalized expression over here that we wrote to start with, g sub n equals negative 2. Now I know r, negative 4 to the n minus 3. So there's my general equation. Okay, and then use that equation to find g sub 11, or find the 11th term. Okay, negative 2 times negative 4 to the 11 minus 3. We'd use our calculator to do that. Okay, you get a pretty decent sized number there. Right, so those are the toughest. Okay, when you don't know the rate of change, you have to find it. All right, and you can't do it like you would in a linear function. You've got to plug it into a generalized equation using the points you have and solve. Okay. Question on that. That's a little weird. Okay. Well, if you've not paid any attention to the bottom of your notes, it talks about Mr. Passwater. He's the guy who writes most of the examples that I use, as well as most of the problems on the test that I use, because he writes for AP. I have a really good feeling he wrote your test that's coming in May. Okay, so a wild rumor spreading that Mr. Passwater won third place in the World's Strongest Man contest. He obviously, if you knew him, you would know that was a lie. The number of people that have heard the rumor can be modeled by a geometric sequence where the 43 people had heard the rumor on day 3 and 140 people had heard the rumor on day 6. So let's kind of walk through that. So that would be A sub 3 would equal 140. No, A sub 3 would be 43, sorry. And A sub 6 would be 140. Okay? So we want to, according to this model, how many people to the nearest whole number have heard the rumor by day 10? Okay? So it's spreading pretty quickly there. All right? He tells us it's a geometric sequence. So we're going to have to follow that same process we just did a few minutes ago. All right? And let's just kind of walk through that. If we start with the lowest value, we know A sub n is going to equal 43 times r to the n minus 3. Okay? But I happen to know A sub 6. Okay? So I'm going to plug in that point. So I know 140 is going to equal 43 times r to the 6 minus 3. So there again is an equation we need to solve. Right? So I have 140 equals 43 r to the third. R cubed is going to equal 140 over 43. Now, I don't know about you, but that does not divide real pretty. All right? And we want to keep as much precision and accuracy for as long as possible. All right? So my rate is actually the cube root of 140 over 43. And let me write that nicer. There's no law that says you can't have an ugly rate. Okay. It can be just as nasty as they want it to be, okay? Especially because this would be a calculator-based question on your AP exam, all right? So now we want to find the number of people on day 10. Well, we're just going to plug that ugly number in to that original equation that we have up here that we wrote right there, okay? So I'm looking for A sub 10. It's going to be 43 to the cube root of 140 over 43 to the 10 minus 3. Now, do you know how to get a cube root on your calculator? Okay. There's a couple of ways to get there. Alpha window is one of them. Okay, and it's down there.
Oh, okay, yeah.
Okay, and you can put the 3 in there for the cube root, or it's just there
It's
on the
also-
menu.
This is the math menu, right?
Yep, and it's also on the math menu. Right? So there's multiple places to get a cube root. Alpha window or the math menu. Okay? The math menu has a plain old cube root, which is nice. Okay. Okay, as much as some days I feel like 0.75 of a person, we really can't have that. So what would we say is our number of people? Yeah, 676. Okay. That's the kind of problem I would fully expect on the AP exam. Right? Probably in a calculator, multiple choice. Just to throw it out there. It seems terrible right now, but I promise after you've done a couple, you'll be like, oh, okay, that's not so bad. Okay. Do you have a question to go with that inquisitive look?
I don't know how you got that out of the calculator. Mine got,
So do 43 parentheses. Oh, did it give you scientific notation? Are you in float mode?
don't even know what that is.
Okay, go to mode. All right, you're in float. That's good. So go back to your home screen. So second click. Yep. All right, 43. Okay. Gonna be done. All right. If you think about a linear function that you know something about, okay, this is my starting term, a sub 0. D is my common difference or my rate of change. And N, what's that the same thing as?
Oh,
It's slope-intercept form.
B plus N.
Okay, it's slope-intercept form. We rearrange the order, but it's slope-intercept form. Okay, so making a connection between good old Algebra 1 and good old Algebra 2. All right. The second one, we already did that one. Nope. Okay, that's point slope form. Okay,
is that an I?
it is. Okay, the reason we use I is because it doesn't necessarily have to be x sub 1. It could be any x value we know, x and y value. Okay, to be any one of them. Okay, so it's just slope-intercept form, your formulas for your arithmetic sequences, slope-intercept form, and point-slope form. Okay, if you're better with the algebra, think about it in terms of the algebra, all right, than the sequence. All right, but it works the same. It's exactly the same. Are you freezing? I was sweating a while ago, like literally running down my neck and back. Sucks getting old. Okay. All right, let's look at geometric sequences. We're really close to being finished. Oh my gosh. Rah. Rah. She said, thank God. All right, I still love y'all. Exponential functions, just y equals a times b to the x. That's the exponential function you've been looking at since you started looking at exponential functions. That's what that general form, all right, of your geometric sequence is. Okay, a being your initial condition. All right, what is the 0th term? Okay. And then likewise, if we look at it, if we don't start with the 0th term, we start with y sub I, some y value that we know, my common ratio, all right, or my b, I'm just going to put b there, okay, to the x minus x sub I, whatever x value went with that y value we put up there in front. Okay, so just making that connection there. All right, you're going to use the geometric sequences and the arithmetic sequence formulas, but they are related to what you knew about algebra. Okay, now the last thing that they'll ask you to do is to look at a table of values and justify if it's linear or exponential. Okay, and they're very specific about the wording for how you justify it. Okay, it was one of the things they really harped at us on this summer when we were in training. Okay, we know a linear function has a constant rate of change. Okay, so we say over equal length input value intervals. Okay, so over equal length input value intervals, the output values change at a constant rate. Okay, at a constant rate. That change is based on addition. Okay, so it's going to be really critical here in a second when we're writing our justifications. All right, over equal length input, those are your x's. The output, the y's, change at a constant rate. Okay, so the y's change equally as the x changes equally, right? With exponential functions, same thing. With equal length, perfect, Megan. All right, with equal length input intervals, the output values change proportionally. Okay, that means we're using multiplication. So every justification, all right, for linear versus exponential is equal length inputs, how does the output change? Okay, so over equal length inputs, how does the output change? Okay. So let's take a look at a couple of tables, and if we don't get to the back side, I don't care. It's just an extra example for fun. Okay? Right. So let's look at these. All right. So the first thing I want to look at is what's happening with my inputs, with my x's. How are they changing? How are my inputs changing?
By 3.
By 3, okay? And they're all 3, so that's great, okay? How are my outputs changing? They're going down by 2, okay? But they're all changing the same, right? So here's what we say. Is that linear or exponential or neither? It's linear. Here is why. Okay? We would say over equal length input intervals. F of x, you could even say the outputs. Yes. Change at a constant rate. Okay. It is linear. Our justification over equal length input intervals. F of x changes at a constant rate. Okay, or the outputs change at a constant rate. You will use that sentence stem every time. Okay, very specific. Great. Let's look at the next one. Do we have equal length input intervals? Yeah, they're all changing by 1. All right. Let's look at our outputs. 1, 3, 5, 7. I couldn't count for a minute. Okay. Now, the question becomes, they obviously are not linear, all right, because they didn't change at a constant rate, but are they proportional? Well, do I multiply the same thing each time to get to the next number? No. Okay, so this is neither. Start with the first part again. Over equal length. Input intervals. The outputs. Change is neither constant or proportional. Okay, seems like you wouldn't have to write that many words, but I'm going to tell you they won't give you the credit of the point, all right, on the free response without them. That over equal length intervals is going to be important, okay? And then proportionally or constant. All right, last one. Okay, if you had to guess, all right, without even starting, how do our inputs change? They change by 5 every time, okay? They go up by 5. Now, take a look at your outputs. I have a change of 40, a change of 20, a change of 10, a change of 5. Okay, is that proportional? What's happening to go from 80 to 40? What are we doing? We're dividing by 2. Okay, that's what we talk about when we say it's proportional. All right, so because that happens, we say exponential. Over equal length input intervals. The outputs change proportionally. And it typically doesn't ask you to explain how they change proportionally. just to recognize that it does. Okay. Now, I don't want to take the time to go through that example that's on the back page, but it's very doable, all right? It asks you to compare the difference between a linear and an exponential function. Now, just knowing what you know about the two, who grows quickest? Typically the exponential. It just depends on what's happening, right? So this one's about two trees or two vines and how they grow. And how would I find where one overtakes the other? What would I look for? Where they intersect, okay? So that's where, if you look on there, it has a calculator-based question on there. That's what it's about, okay, on that last example. I recommend you take a look at it. I'll try to fill it in on my notes before I hit submit so that you guys have that to look at. But let's look down. Here's what I'd like for you to do as lesson practice, okay? So 2 worksheets, okay, not a ton, all right? Worksheet A for 2.1, just to practice all the different things we talked about, 2, 4, 8, 10, 12, 14, 15, and 17. Okay. And then worksheet A for 2.2, that's got the tables and some application word problems, 1, 3, 4, 5, 6. Okay. And that's it. Tomorrow your project's due. Okay, you can bring it in first thing in the morning if you like. Okay, and your quiz retakes are tomorrow. Quiz retakes are due tomorrow. All right, good job. Tomorrow we're going to cover 3 sections. It's all things exponential functions. Okay, so we're going to rock right through that. Okay.